Okay, to repeat what I said, I'm not sure I stopped the last before. Stokes theorem is a lot like Green's theorem. It applies just to plain regions. So Green's theorem applies just to plain regions. Stokes theorem applies to regions that aren't in the plane. Okay. Green's theorem tells you that the circulation around the region, and we did pretty much prove that for a small rectangular region with sides parallel to the coordinate axis. Okay. If this interval is non-zero, then you have a circulation. Okay, you shrink this down to take a limit. You know, it's a total area of this thing, and the length and width both approach zero. You get a limited value of the circulation, and that's the curl. Okay. So the path integral you get is a measure of the total curl within the region. And if this is the region, you can break it up into small regions. And as we did before, every region has a net circulation interval that's zero, because for each region, circulation measured in this direction on this boundary site is equal and opposite to the circulation measured in this boundary, because the two boundaries go in opposite directions. So for any of the regions of totally interior here, the net circulation, if you wish, has to be zero. Okay. Except, well, and that's for an interior region. The region that isn't interior, well, here's a region. Circulation of this boundary is in common with this region, so it cancels out. Circulation on this boundary is common to this region, so it cancels out. But circulation around the circulation along the third side cancel out. What happens all along the boundary? So the total circulation around the boundary is equal to the interval of circulation within. Meaning, if this is a three-dimensional region, still works. It's a surface embedded in three-dimensional space. A surface is not a plane. It's a well-behaved surface, well-defined surface, orientable, and you have a reasonable function, a vector function. It's still going to work. And the statement of the theorem then is that the integral around the boundary of f dot ds, just a line in the middle here, is equal to the integral of the current over the curl, equal to the integral of the curl over the entire interior of the region. Okay. Reminding you that these regions are typically set up in terms of the cross product of the T and T vector. So we essentially have we have a parameterization. We parameterize any surface in terms of U and V or any two variables. Okay, at least any surface of which Stokes theorem would apply. Okay. So just did this. Some people have some trouble. And most people have trouble, at least a couple of problems on the whole. So we'll do some examples of these to try to reiterate what's going on with this parameterization. Also, I'd like to mention, you got your work written out. If you had any problems, it'd be great if you could get me a copy of that book so I can spot what you did wrong, which I can't tell much if you're wrong answer. Okay. So I can't tell where you're doing any difficult. Everybody got some problems. Well, and some with problems. But not everybody will know it all problems. Okay. So anyhow, now we pose, okay, if f is gradient of scalar theory, And the curl of that is cross product of the Bell operator. Well, that's always new. You should be able to prove that. You can simply write out Del F, and the Del F, you have I during K. It becomes this. If you multiply this out, everything cancels. And you should be able to do that. That way, if you ever forget, wait, curl of the gradient really zero. Okay. I mean, you can see it. On the I, you're going to have the partial of FZ with respect to Y, like FZY, and here you're going to have a minus FYZ. That's zero. Right? For the J component, you're going to have FXZ minus FZX. Okay. If you just write it out, you say it's got to be zero. Just know that FXZ is equal to FCX. The order of differentiation makes no difference. Okay. So that's very easy to prove, very easy to see, very easy to understand. Well, how does that apply to Stokes theorem? Tells us that the circulation, or that the line integral around any closed path has to be zero. Right? Well, that means that is a conservative function. Conservative vector function. Okay. So there's a roundabout proof through Stokes theorem that proved it right. Okay, since this is zero, because of this, this is zero. So F is conservative. Of course, conservative vector field is exactly one that's equal to the gradient of the scalar. The potential function of the vector field. That kind of gives us a connection. It's something that we should have some pretty good understanding of. Okay. Now, pause for a second. Okay, now what I see is everybody has chosen to parameterize, not to parameterize, to describe a triangle in the XZ or YZ or XY plane. Okay. If there was many qualities. Well, that would be great if we were integrating over this triangle. We are. We're not integrating anything over this triangle. So let's just look at the XY plane, for example. Well, we have 6 here, 4 here. I can shift it all the coordinates. So here's the path. And if the path is going in this direction, well, it's going this direction. And right there is the path C1. No, I'm going to say that if x equals 6 minus t, because we're going in this direction, that would be the negative direction. That x equals 6 minus t, t from 0 to 6, would take us from t equals 0, x equals 6, right? T equals 6, which would make x equal 0. The t goes from 6, or x goes from 6 to 0. What's y equal to? Well, y's going to go from 0 to 4. Okay. Now, t's already gone from 0 to 6, so we can't have t going from 0 to 4. Y equals 2/3 t. Okay. Because then when t equals 6, y would equal 4. When t equals 0, y would equal 0. And these are both linear, they're going to give you a straight line. Okay, so that would be a parameterization of C1. How would you parameterize C2? How would you parameterize C3? I could also write this a different parameterization. We're going to let S go from 0 to 1. S isn't good to do the S. Not like T, U, V. I don't have a good letter to use. Still want to do it. So I'm just going to use. I like R because we use that for vector. Okay. X is going to be 6 times 1 minus p. But my parameter is going to go from 0 to 1, which makes things kind of easy. It makes this a little more involved, but it's not difficult to see. When p equals 0, x has to be 6. Okay. And we're going to retrograde that's 1. When p equals 1, x is going to have to be 0. P goes from 0 to 1. Right. To be pretty clear, just by inspection, the 1 minus p is going to go from 1 to 0. And if we want to go from 6 to 0, then we just need 6 times that. Okay. So kind of use that. And then y goes from 0 to 4. Okay. You know, if you get used to thinking about this, and you really do need to be able to do this kind of parameterization, you understand the advantages of both. Okay. Now, the integral over f C1 what? Well, f is yes, right. The other thing is, we do have Z, right? What can you say about Z here? Well, you're in the X, Y plane, 0, right? Either parameter Z, Z is going to be 0. Now I'll use this parameterization. This is closer to the way y'all have thought it through. Which code is here, kind of irritating and showing, which is okay. It worked. Okay, but now is X plus Y times I. Okay. Well, X plus Y is this. Okay. And of course, T is going from 0 to 7. Then it's going to be plus Z minus 2xj. Well, Z is 0. 2x is going to be 2. 2 times 6 minus tj. Then Z plus 3y, y is 2/3. Hey. What's yes? Fortunately, you should start her up higher and leave yourself room. But the yes is X prime I plus Y prime Z plus Z prime K, which is negative I plus 2/3 J. Yes, that was pretty bad. Then it's that. And you can understand do better. Well, if we do that dot product, is about to have not quite. Okay. It's going to be the negative of this. This is 6 minus 1/3 t. Anti-grid is going to be 6t minus t squared over 6. Okay. And from 0 to 6, well, you can work it out. Okay, well, that's how you set this thing up. Okay. You do the same thing on all 3 boundaries. Now, there's one advantage to having a single parameter for all 3 of these lines. And, you know, that's what I'm doing. This stuff I did with B here was off the screen. But again, using a parameter P that goes from 0 to 1 and using the same parameter on all these integrals allows us to just write a single integral, combine everything into something at some point. And that could have an advantage, although it's not difficult to do it like this. Okay. Well, that's getting to be a pain, isn't it? So it's not difficult, but it's a pain. We can, that's something we want to verify Stokes theorem. I'm not going to finish the verification yet. We're going to do the curl del dot data. Okay. Now, I'll use the determinant. Little abbreviation for the partial respect to x, partial respect to y, partial respect to z. I've got x plus y here. I've got z minus 2x here. And I've got z plus 3y here. It might be a little small, but you can write it out just as easily as I can, okay? So that's a calculation we need to do. We're going to have I times the partial of this with respect to y minus the partial of this with respect to z. Well, the partial of this with respect to y is 3. The partial of this with respect to z is 1. So it's 3 minus 1. We get 2i. On j, partial of this with respect to z is 0. Partial of this with respect to x is 0. So we get no j. Okay, partial of this with respect to x is negative 2. Partial of this with respect to y is 1. It's this minus this. So it's going to be minus 3k. Okay. Parameterize this, but I guess I will. There's a parameterization. And this might actually equal u, y will be, and then z, which should be 12 minus 2x minus 3y, will be 12 minus 2u minus 3. Fair enough? Okay. That parameterization, see what you do. So you get the percent. Ooh, none of that was recorded. Okay, I'm not sure what we've done. But for this example over here, the TU is partial respect to x times y, respect to y times j, partial respect to z times a. That ends up being I minus 2k, and it's very easy to calculate those. These are pretty simple functions. Okay, and then TV would come out to the sum cross product, be this, right? Cross product. Okay. So we're not going to continue this because it's taking a while to get through this. Going to go to another example. Graveloid. Here. Now, it's parabola of revolution y to z squared. About the one axis. Parameterize that. Well, let's just bring this back. That's why you see that this circle here, if you can parameterize the interior of this circle, and then let y equal whatever radius we get. I don't want to talk too much about that. I have to draw for. This should be a familiar parameterization. Parameterized in terms of x, y, and z with the parabola opening in the z direction. Pretty obvious. When parameterized concentric circles in the x, y plane. Now, some people we get over it. I don't want to over explain that right now. It should be pretty clear that we let x equal u cosine b, z equal u sine b. Then we're going to go in the counterclockwise direction around circles of radius u in the x-z plane. In the biggest circle, we're going to have the radius that leads us out to where y equals 4. And I don't know if I did this on the video, but this thing's cut off here in the frame of y equals 4. So z is u sine b, x is u cosine b, y is going to be u squared. Okay. B is going to go from 0 to 2 pi. Y can be a maximum of 4, so u has to be a maximum of 2. We're going to have 0. Less or equal to 2, less or equal to 2. Careful parameterization. Now, if we're going to do an integral, we haven't even gotten to setting up Stokes theorem. But we've got this circle here, it's a boundary. We've got a line integral over the circle. We've got the surface bounded by that circle, which is the paraboloid. We got our du equals good shape. CU is going to be okay. Now the partial depth with respect to u is cosine b sine b to is straightforward. They can prove these with respect to u. And TB is the partial x with respect to b, which is negative u sine b on plus I've got the y and the z there. Do you here, sine b here. Used to do the X, Y, Z orders. And then the partial of y with respect to b is going to be 0. And then we're just going to have u cosine 3a. And then TU cross 3b. Here's what it is. And then we're ready to set up the integral. Okay. Now, we're kind of a little bit hung on the idea of parameterizing surfaces. Okay. We're getting there. But we gotta get there a little better and then apply it to these Stokes theorem problems. Once you have that, there's still a lot to learn about Stokes theorem. So, I was hoping to use all next week for review. We're gonna have to overlap Stokes theorem into Thursday's class. We'll still leave some time for review, but we'll see what we can get done. So kind of review how we parameterize surfaces. As I said, that's a challenge. We talked about it in some detail last time, why you do what you do. Probably need to get your hands on more problems and write them out. Okay. So we'll go from there.